Somewhere in the asteroid belt right now, there are rocks older than the Earth itself. Not older by a few million years, older by hundreds of millions. Some of them formed before our planet existed, before the sun had finished igniting, before any of the material swirling around it had clumped together into anything recognizable as a world. They are the leftovers, the unchanged remnants of the raw ingredients that built everything we know. And locked inside them, in their minerals, their chemistry, their ancient dust, could be the answer to one of the most profound questions humanity has ever asked. Where did life come from? For decades, scientists have been staring at asteroids from a distance, running radar scans, capturing photographs, building computer models, and all of that has been enormously useful. But there is a hard limit to what you can learn about something without actually touching it, without bringing a piece of it home. That's exactly what one mission set out to do. A spacecraft that would travel hundreds of millions of kilometers, drop down to the surface of a spinning asteroid, grab a fistful of ancient material, and bring it back to Earth without contaminating a single grain. It was called OSIRIS-REx, and what it found when it got there changed everything we thought we knew about the early solar system, and possibly about the origin of life itself. Here's the full story. To understand why this mission mattered, you first need to understand the problem with the asteroids we already have. Every year, space rocks fall to Earth. Meteorites land in deserts, in fields, in Antarctica's ice sheets, and occasionally through someone's roof. We have thousands of them in collections around the world. Scientists have studied them extensively, but every single one of those meteorites has been compromised. The moment a space rock hits Earth's atmosphere, it's traveling at tens of kilometers per second. The friction generates temperatures hot enough to melt iron. The outer layers burn away. The chemistry changes. Then it hits the ground, gets buried in soil, absorbs moisture, reacts with oxygen. By the time a scientist picks it up, even hours later, it is no longer what it was in space. The only way to get a truly unaltered sample is to go and get it yourself. Collect it in space, seal it in a protective container before it ever touches atmosphere, and bring it home under controlled conditions. Japan's space agency JAXA had already attempted this twice with their Hayabusa missions, both times returning tiny quantities of asteroid material. NASA had never done it. OSIRIS-REx was going to change that. The mission launched in September 2016, part of NASA's prestigious New Frontiers program, the same program that sent Juno to Jupiter and New Horizons past Pluto. Its target was an asteroid called Bennu, a 500-meter-wide lump of ancient carbon-rich rock in an orbit that occasionally brings it uncomfortably close to Earth. Bennu was chosen for several reasons. Its orbit made it reachable. Its composition, a type called carbonaceous, meant it was chemically primitive, likely unchanged since the dawn of the solar system. And its size put it in an interesting category, large enough to have potentially retained water-bearing minerals, small enough that its surface might preserve material from the very beginning of planetary formation. Scientists had already built a surprisingly detailed picture of Bennu before the spacecraft ever left Earth, using decades of radar observations. They knew its rough shape, a spinning top, wide at the equator, narrowing toward both poles. They knew its rotation rate, its approximate density, its orbital path. What they didn't know was what they'd actually find when they got close enough to see the surface in detail. When OSIRIS-REx arrived at Bennu in December 2018 and began returning images, the mission team got their first shock. The radar models had suggested Bennu's surface would be relatively smooth, fine-grained, sandy almost, the kind of surface you could imagine a sample collector sinking gently into. What the cameras actually showed was a world covered in boulders, not small boulders. Some of these rocks were the size of buildings, 20 meters tall, 58 meters across, sprawling across the asteroid's surface like scattered debris from some ancient catastrophe. The entire asteroid looked less like a uniform rock and more like a loosely packed pile of rubble that had somehow held itself together under its own minimal gravity. This created a serious problem. The mission plan called for finding a clear patch of surface roughly 25 meters in diameter, with particles no larger than a centimeter, where the sample collector could safely make contact. On a world this boulder-strewn, such patches were rare. The team spent more than a year in orbit, 505 days in total, meticulously mapping every square meter of Bennu's surface, eventually narrowing their options down to 4 candidate sites, each named after a bird to match Bennu's own Egyptian mythological origins: osprey, kingfisher, sandpiper, and the one they ultimately chose for the sample attempt, nightingale. While they were mapping, the spacecraft's instruments were also doing something else entirely, reading the chemistry of the surface from orbit. And Bennu kept surprising them. Spectroscopic analysis revealed the clear signature of hydrated minerals on the surface, clays, materials that contain water locked into their molecular structure. On an asteroid this small, far too small to have ever held liquid water on its own surface, this was unexpected. It suggested that Bennu had formed somewhere else entirely, that at some earlier point in its history, it had been part of a much larger body, a body that had water, a body that had perhaps been genuinely wet. Then there were the particle ejection events. Bennu, this seemingly inert lump of ancient rock, was occasionally flinging material off its own surface. Not violently, not catastrophically, but consistently. Small rocks and dust particles would detach from the surface, drift around the asteroid in loose orbits for a few revolutions, and then either escape entirely or settle back down. OSIRIS-REx, in its orbit less than 2 kilometers above the surface, had to track and dodge this debris. The cause, scientists concluded, was the asteroid's rotation. Bennu spins fast enough that centrifugal forces at its equator exceed the minimal gravitational pull holding surface material in place, and that rotation is gradually accelerating, driven by the tiny but persistent pressure of sunlight on its irregular surface. Given enough time, Bennu might eventually spin itself apart entirely. But that was a problem for the distant future. In October 2020, OSIRIS-REx had a more immediate task. The sample collection maneuver, officially called Touch and Go, or TAG, was one of the most precisely engineered operations in the history of robotic space exploration. The spacecraft couldn't simply land on Bennu. The asteroid's gravity at the surface is roughly 100,000 times weaker than Earth's. There is no meaningful landing on something like this. Instead, OSIRIS-REx would descend slowly, extend its sample collection arm, a device that looked like a car's pogo stick fitted with a disc-shaped collector head, make contact with the surface for a matter of seconds, then immediately fire its thrusters to pull away. During those seconds of contact, a burst of pressurized nitrogen gas would be fired downward, stirring up surface material and forcing it up into the collector. The whole sequence had to be autonomous. The signal delay between Earth and Bennu meant real-time control was impossible. Any instructions sent from mission control would arrive too late to be useful. The spacecraft had to execute the entire maneuver using its onboard computers, making decisions based on pre-programmed parameters and real-time sensor data. In April 2020, OSIRIS-REx ran a practice descent, dropping to 65 meters above Nightingale before pulling back. Everything worked. In August, a second rehearsal brought it to 40 meters. Still perfect. On the 20th of October, it went all the way. Moving with extraordinary slowness, it took hours to descend from its operational orbit. The spacecraft oriented itself, raised its solar panels upward and out of the way to protect them from debris, and extended its sample arm toward the surface of Nightingale Crater. The arm touched down, and then, instead of stopping, it kept going. Bennu's surface, it turned out, had almost no structural integrity at all. The material the spacecraft touched was not compacted rock. It was more like a collection of loosely stacked gravel held together by barely anything. When the sample arm made contact, it sank almost half a meter into the surface, and when the nitrogen burst fired, it didn't stir up a little dust. It blasted a crater into the side of the asteroid, sending more than 6 tons of material fountaining outward in all directions. OSIRIS-REx's thrusters fired hard to pull the spacecraft away from the expanding cloud of debris. It had punched a hole in Bennu. When the team checked the sample collector, they found it had captured somewhere between 400 grams and over a kilogram of material, more than 10 times the minimum mission goal of 60 grams. So much material, in fact, that a rock fragment had wedged itself in the collector's closing flap, causing some small amount to leak back out into space before the head could be sealed. The sealed sample container was then transferred into the return capsule and locked away for the journey home. OSIRIS-REx departed Bennu in May 2021 and spent the next 2.5 years crossing the inner solar system. On the 24th of September 2023, it released its return capsule from approximately 100,000 kilometers above Earth's surface, then fired its own engines to divert away from our planet and begin an entirely new mission. The capsule hit Earth's atmosphere at 43,000 kilometers per hour, making it the second fastest human-made object ever to re-enter, enduring deceleration forces 32 times the pull of Earth's gravity. Its heat shield reached temperatures of around 2,700 degrees Celsius, roughly half as hot as the surface of the sun. Inside, the Bennu sample was kept below 75 degrees by an advanced ablative heat shield, a material that sacrifices its own outer layers to carry heat away from the capsule interior. 2 parachutes deployed in sequence. The capsule floated down through clear Utah sky and settled into the desert with a gentle thump, right on target. Inside, 120 grams of pristine asteroid material, unheated, uncontaminated, exactly as it had been on the surface of Bennu. Or so the team hoped. Getting into the capsule turned out to be its own challenge. 2 of the 35 fasteners holding the sample canister shut had been infiltrated by Bennu dust during collection, effectively stripping their threads. The existing toolkit at NASA's Johnson Space Center couldn't open them. Engineers had to design, fabricate, and test an entirely new screwdriver, built from non-magnetic surgical steel, small enough to work inside a nitrogen-purged glove box, before they could access the main sample. 3.5 months after landing, they finally got inside. An additional 51 grams of sealed, pristine material was waiting for them. Combined with material that had escaped from the sample head into the capsule during the return journey, the total haul exceeded 120 grams, more than twice the original mission target. At least 70% of it will be preserved untouched for future generations of scientists using analytical tools that don't yet exist. The rest went to more than 200 researchers at laboratories around the world. What they found inside that material has rewritten scientific understanding of the early solar system. The first surprise came quickly. The sample was extraordinarily rich in carbon and nitrogen. Then came the organic chemistry results. Scientists identified 15 of the 20 amino acids that form the basis of all known life on Earth. They found all 5 nucleobases, adenine, guanine, cytosine, thymine, and uracil, the chemical letters that spell out genetic information in DNA and RNA. They found essential sugars, including ribose, the backbone molecule of RNA, and for the first time ever detected in an extraterrestrial sample, glucose. A team from Tohoku University in Japan made another discovery. The relative abundance of ribose over deoxyribose in the sample supports what's known as the RNA world hypothesis, the idea that the earliest life on Earth used RNA rather than DNA as its primary information storage molecule. Finding this signature in an ancient asteroid strengthens the case that the building blocks of this early biochemistry were delivered to Earth from space. Then came something nobody had seen before. Researchers at NASA's Ames Research Center found a material they nicknamed space gum, a polymeric substance rich in nitrogen and oxygen, layered onto mineral grains inside the asteroid in thin sheets barely thicker than a human hair. Its chemical structure, when analyzed using electron microscopy and X-ray spectroscopy, bore similarities to polyurethane, but far more disordered, far more random than any manufactured plastic. This material had never been detected in space before. It may represent a class of complex molecule that helped trigger the chemical reactions leading to life. Critically, none of these fragile compounds would have survived atmospheric re-entry. They would have been destroyed at the temperatures a meteorite experiences falling to Earth. The only reason scientists were holding them was that OSIRIS-REx had brought them home safely, protected the whole way. Water was everywhere in the sample too, not liquid water, but evidence of it. Clay minerals. Serpentine, a rock type found at mid-ocean ridges on Earth, where molten material meets seawater. Pyrrhotite, an iron sulfide that forms near hydrothermal vents. Phosphates, a molecule critical to DNA, which forms only in the presence of liquid water. The picture that emerges from all of this is striking. Bennu almost certainly originated from a much larger body, a parent asteroid or protoplanet that was warm, wet, and chemically active. A world that had hydrothermal systems. A world where water and rock and organic chemistry were interacting over long periods of time. Not life, not yet, but everything that came before it. Scientists at Johnson Space Center also found that Bennu's dust contained presolar grains, microscopic crystals that condensed before our sun ignited. Analysis showed signatures of small and medium-sized stars, but also of supernovae. The sample contained 6 times more supernova dust than any other space material ever studied on Earth, evidence that our solar system was seeded by multiple generations of dying stars before a single planet formed. The questions this mission has raised will keep researchers busy for decades. Did Earth's water come from asteroids like Bennu? Did the amino acids that assembled into the first proteins on our planet arrive on the backs of ancient impacts? Is the chemistry of life not a local accident, but a universal abundance, scattered across the solar system, waiting for the right conditions to organize itself into something that breathes? OSIRIS-REx itself isn't done asking questions. 20 minutes after releasing the Bennu sample capsule, it fired its engines and redirected toward a new target, Apophis, a 370-meter asteroid that will pass within 50,000 kilometers of Earth in 2029, closer than some of our own satellites. The spacecraft, now renamed OSIRIS-APEX, will spend 18 months studying Apophis, mapping its surface, analyzing its chemistry, and watching what happens to an asteroid when Earth's gravity stretches and pulls at it during a close flyby. It will also repeat its signature move, dipping to within 5 meters of the surface and firing its thrusters to churn up material from below. A mission that began with a 60-gram target returned more than 120 grams of the most scientifically significant material ever brought back to Earth. It found the letters of the genetic alphabet floating in ancient asteroid dust. It found the chemical fingerprints of hydrothermal systems on a world that no longer exists. And it did it by reaching out, gently, precisely, across hundreds of millions of kilometers, and simply picking something up.